To run your app on an actual iOS device, we need to shift from our development environment in Xcode to the handheld devices that users will eventually interact with. While the simulator offers some great initial testing capabilities, it simply can't replicate everything. Today, we're going to explore the ins and outs of running your app on a real iOS device and the benefits that come with testing hardware components and software APIs. So far, we've learned about downloading and installing Xcode as an essential first step for iOS development. We talked through obtaining Xcode from the Mac App Store and getting it installed. All that includes agreeing to a license and setting up necessary components. We also created a new project, set up our app's interface using Storyboard, and even wrote some initial Swift code to build and run our first application. And let's not forget, we introduced user interaction with a button and discussed the potential of using Swift UI for more intuitive UI design in future projects. Now, let's dive into how to run your app on an iOS device, which will allow you to see real-world performance and behavior. First things first, make sure your iOS device is ready. You'll need either an iPhone or an iPad with the latest version of iOS installed. Connect your device to your Mac using a USB cable and ensure you can access it through Xcode. If this is your first time connecting your device, you might be prompted to trust the computer on your iPhone or iPad. Just follow the on-screen instructions and, make sure you unlock your device if it's locked. Once you've trusted it, your device will show up in the list of devices in Xcode. This displayed horizontal bar chart, titled Time to Run Your App on an iOS Device, lists 6 sequential setup steps on the vertical axis and shows the time in minutes on the horizontal axis. Each step is annotated with its integer minute value. Connect device, 3 minutes. Trust computer, 2 minutes. Launch Xcode, 1 minute. Select device, 4 minutes. Run app, 10 minutes. And trust certificate, 2 minutes. From this visualization, we can draw several clear conclusions. The single longest step, run app, takes 10 minutes, which accounts for roughly 45% of the total summed time of 22 minutes. This indicates that deployment and runtime syncs are the dominant time sinks. Then we have select device at 4 minutes and connect device at 3 minutes. These come next in the hierarchy of time consumption, while launch Xcode, being comparatively quick, only takes a minute. Now, if we group the two trust-related steps, trust computer and trust certificate, they total 4 minutes, which actually matches select device on its own. These patterns highlight that while some preliminary steps are quick, the actual deployment and run phase is where we see the bottleneck. So that's definitely something to focus on when estimating total setup time or troubleshooting delays. Oh, and those annotated bars make it super clear where you should prioritize optimization efforts. This way, you can effectively reduce overall setup duration in the most impactful manner. Now, let's see how we can implement the necessary permissions for accessing the user's location in our app's configuration. In the info.plist file, which is key for defining the app's settings, we need to specify the key NSLocation when in use usage description. This key is really important because it lets the user know why our app needs access to their location while they're actively using it. Following the key, we provide a string. This acts as a descriptive message. The aim of this message is to clarify to users why we're requesting their location data, assuring them that accessing their location will enhance their experience with the app. Now, it's crucial to craft this message thoughtfully, as a clear and informative description helps build user trust and encourages them to grant the necessary permissions. Remember, iOS will prompt users for permission when they try to use location-based features, so the message you provide can really influence their consent. By setting up this key value pair in info.plist, we're ensuring that our app meets the requirements for accessing that sensitive user information while being transparent about its intentions. Next, let's build our app. Click the Run button located at the top left corner of your Xcode window. It's going to compile all that app code and install it on your connected device. Now, just a heads up, the first time you run it, this process might take a few moments. That's because Xcode has to set up various components, so just hang tight. If everything goes smoothly, you'll see your app open on the device automatically. But, if something goes wrong, don't panic. Xcode will provide error messages or alerts. Pay close attention. Common hiccups can come from the development team configuration or device provisioning issues. If your app isn't deploying correctly, just go to the project settings and double-check that you've selected the right development team. This is crucial for code signing, you know? Once your app launches on the device, dive in and interact with it just like any user would. Test all the functionalities. Tap buttons, swipe through views, and enter some data. You know, it's so important to see how it performs in the real world, especially when it comes to user experience and speed. You might even catch things that you didn't notice while using the simulator. For instance, remember that hardware-dependent features like the camera or GPS will only work when you're running your app on an actual device. Now, let's take a look at how we can implement a simple data management solution within our view controller. In this example, we define a class called myViewController, which inherits from UIViewController, so we can utilize all the features provided by UKit for building an interactive user interface. Within this class, we declare a variable called dataArray. It's an array of strings that will be used to store data in memory. This array serves as our data model. Now, when the view loads, the viewLoad function gets called, triggering the loadData method. This method showcases a simple loop that populates the data array with 1,000 items, where each item is labeled item followed by its respective index. While this implementation works well in a controlled environment like the simulator, it's absolutely essential to profile memory usage on an actual device using instruments. We want to ensure that such data handling doesn't lead to memory issues, which can be cumbersome. By profiling, we can assess how the application performs under real-world conditions, making adjustments as needed to optimize user experience in the final app. So let's keep that in mind as we move forward with our project. Now, let's implement a function that allows us to fetch data when a button is tapped. In this code, we define an action connected to a button in the interface using the @iBackground keyword. This means the function will be triggered the moment the user interacts with that button. When the button is tapped, the function captures the starting time using date, which will help us measure how long the fetch operation takes. Then we call fetchData, which is presumably a function that retrieves information from an API. This function takes a closure as a parameter, enabling asynchronous behavior. That means the app won't freeze while it's waiting for the data to come back. Inside the closure, we calculate the elapsed time by subtracting the start time from the current time. This helps us understand how efficient our data fetching is going. Then we use print statements to log the elapsed time and the response data to the console. This is super useful during development because it allows us to track the app's performance in real time on an actual device. Monitoring these logs can help us diagnose issues and optimize network interaction, ensuring a seamless user experience. User interface interactions are also a critical area of testing. Your app may look perfect on the simulator, but let me tell you, the touch interactions, well, there's something entirely different on an actual device. So take the time to test gestures thoroughly. You know, tapping, swiping, and pinch to zoom if your app implements such features. Real-world latency and response issues often creep in here. Make sure that all touch targets are large enough for users to interact with easily. Testing on real devices can really reveal hidden problems that you might miss if you're only using the simulator. Now, as your app interacts with services like location, the camera, or Health Kit, it's vital to test these interactions on an iOS device to truly gauge how they perform under various conditions. For instance, switching between foreground and background while using location services can impact how your app maintains an accurate location, which is definitely something you need to keep an eye on. So make sure you're thorough in your testing. It could save you a lot of headaches down the line. In summary, running your app on a physical iOS device is a crucial step in the development process. Now, the simulator, it's a fantastic tool for initial testing, no doubt. But real devices reveal those little nuances in performance, user interface behavior, and hardware interactions that the simulator simply can't fully emulate. By leveraging Xcode's capabilities for compiling, provisioning, and debugging, you can ensure that your app isn't just functional on a theoretical level, but truly performs seamlessly in the real world. Engaging with your app in this manner will really enhance user satisfaction and retention, leading to a more polished, finished product. From testing memory management to optimizing touch interactions, every detail, dramatic pause. So now, strap in and let's explore this fascinating journey of app deployment. Watch as your code transforms into reality on actual devices.